This will be for the Kuta software worksheet, tangents to circles. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So right here we have a circle. Q is the center, and this line right here is the radius. We can call that R. All right, and this blue line right here is the tangent line. All right, and the idea behind this theorem, if this is a tangent line, it has to make a right angle with the radius right at the radius's endpoint that's on the circle. That's point P. But the point is, the radius and the tangent, they make a right angle. They are perpendicular to each other. All right, determine if line AB is tangent to the circle. So let's see, right here is line AB. Okay, and we can assume this is the center. So this right here is a radius. And this right here, I'll do it in a different color. This right here is also a radius. Okay, so if the radius equals 12, this radius right here is also going to be 12. But anyhow, we want to prove that AB is tangent to the circle. If this is the radius and this is the potential tangent, it has to make a right angle right here. All right, so we have a potential right triangle. We want to see if we can prove A squared plus B squared equals C squared. All right, so C is always the hypotenuse across from the right angle. So that's going to be this whole side length here. Okay, so we're going to have to add 8 plus 12 in order to have our hypotenuse. 8 plus 12 is going to be 20. So that is going to be the value for C. A and B, it doesn't matter which is which. I will let A equal 16 and I will let B equal 12. All right, so A squared is going to be 16 squared. B squared is going to be 12 squared. And C squared is going to be 20 squared. All right, I will put a question mark for now because we don't know if it's true yet. Let me go to the calculator. 16 squared plus 12 squared. Okay, and I get 400. Now, 20 squared, I could do that in my head. 20 squared, 2 times 2 is 4. And since it's squared, I just add 2 zeros. If you can't do it, just go to the calculator. Does 400 equal 400? Yes. Okay, so that means AB is tangent. All right. You don't have to write that every single time. You could just write yes or no. But if the Pythagorean theorem checks out, it's yes. If it fails, then the answer is no. This is not a right angle, and that means it's not tangent. All right, please try number 4. I'll give you the setup. All right, so this is AB right here. That is my potential tangent line or segment. And here's the center. This right here is my radius R. Okay, so the radius and the tangent have to make right angles with each other. So this right here is my potential right angle. We want to prove A squared plus B squared equals C squared. All right, across from your right angle is always going to be your C, or the hypotenuse. So C squared is going to be 19 squared. A and B, it doesn't matter which is which. I'll let 11.4 equal A. So that's going to be 11.4 squared. I'll let the other side equal B. So that's going to be 15.2 squared. You don't really necessarily need parentheses, but it looks a little cleaner. Anyhow, we're trying to prove this true. So I'll put a question mark. Let me do 11.4 squared plus 15.2 squared. And I get 361. On the other side, let me do 19 squared. Again, I get 361, so it checks out. The answer is yes. All right, so 2 and 3 are the same thing. Next section, find the segment length indicated. Assume that lines which appear to be tangent are tangent. All right, let's go right to number 6. Now, to me, this one here appears to be tangent, okay? This right here, this is the center. This right here is definitely a radius. All right, and this one right here is also a radius. So if the radius is 1.5 here, it's also going to be 1.5 right there. All right, so again, the line that appears to be tangent is tangent. This is the only one. So since it appears to be tangent, we can assume it is. And if this is the radius, it has to make a right angle with the radius. All right, in order to solve for this side length with the question mark, we need a squared plus b squared equals c squared. So go across from your right angle. That entire side length is your hypotenuse. That's going to be 1.5 plus 1. Okay, so that whole side length is going to be 2.5. Okay, the hypotenuse across from the right angle is always going to be your c. All right, so c squared is going to be 2.5 squared. The other two sides, it doesn't matter which is a or which is b. I'll let the question mark equal a. And I'll let the radius right here equal b. All right, so since a is just a question mark, you can plug in question mark or just leave it as a squared. B squared is going to be 1.5 squared. Now, you could evaluate it from here. Okay, let me erase this so I have some room to work. You can square this, but really, I would just leave it for now. Okay, we're trying to solve for a, so we want to get rid of the 1.5 squared and move it to the other side. The opposite of positive 1.5 is negative 1.5 squared. You want to do the same thing to both sides. Plus minus, it cancels. Bring down your a squared. And I'm going to leave it as 2.5 squared minus 1.5 squared. Okay, we have a squared. The opposite of squaring something is to take the square root. Square root of a squared is just a. And I'm going to do the square root of this whole thing on the calculator. If you want to do this first and then hit square root at the end, that's fine. Some of you can do it just in one step, depending on your calculator. All right, and I get a equals 2. So that was the, if you want, that was the question mark. All right, so 5, 7, and 8 are the same. Just remember right here, this dot is the center. So if you go from center to circle, that's a radius. So if the radius is 6, in this direction, it is also going to be 6. Okay, and then for this side length, the whole side length is going to be 6 plus 6, which is 12. All right, and this will be your right angle right here. The question mark is going to be your value for C, and just use Pythagorean theorem. All right, so you want to remember tangent segments from a common external point are congruent. Let's take a look. All right, so these two line segments here, they're tangent segments. They extend from this common point, which is S. Okay, And if those are both tangent segments to the circle, then they are congruent. So if this is a tangent and this is a tangent, and they extend from the same point, you can mark those congruent to each other. All right, so SR is congruent to ST. All right, in this section, they want us to find the perimeter of each polygon. Assume that lines which appear to be tangent are tangent. All right, let's look at number 9. We're looking to get the perimeter. All right, let's see. Look for the segments here. This one here is 10.5. And extending from the same point, this one here has to be congruent to this one here. So this is also going to be 10.5. This one here is 11.2. Extending from this same point is this tangent here. So if this is 11.2, that one has to be 11.2. All right, and it is indicated that the entire length here is 23.2. So this one here is just going to be 23.2 minus this portion right here, which is 11.2. Okay, and that's going to be 12. If this segment here is 12, then this segment here is also going to be 12. Now, in order to find the perimeter, we just add up the sides. All right, so the perimeter P. Notice every segment has a repeat, 12 and 12, the 10.5s and the 11.2s. So for the perimeter, I'm going to multiply each one by 2. I'm going to do 12 times 2. Then I'm going to do 10.5 times 2. I'll use parentheses so you're not confused with decimal points and times. 12 times 2, 10.5 times 2, and 11.2 times 2. All right, so perimeter is just the sum of the sides. Go to your calculator, and I get 67.4. And that is the perimeter P. All right, please pause and see if you could do number 10, please. All right, look for tangent segments. This one right here. This one right here is 13. So this one right here has to be 13 because they extend from the same point. If this entire side length is 25 and this length right here is 13, then this length right here has to be 25 minus 13. All right, that's going to be a 12. If this one here is 12, then this one here is also going to be 12. If this entire side length is 21.8 and this side length here is 12, this side length right here, this segment is going to be 21.8 minus 12. Okay, that's going to be 9.8. If that's 9.8, then this one right here is 9.8. If this one here is 4.6, this one here is 4.6. All right, I think that's it. Every tangent segment should have a twin in terms of length. All right, so we're going to multiply by 2 once again. We have 2 13s. We have 2 12s. We have 2 9.8s. And we have 2 4.6s. All right, let's go to the calculator. All right, I get 78.8. That is for my perimeter P. Last section, find the angle measure indicated. Assume that lines which appear to be tangent are tangent. All right, so here we have two radiuses or radii. See, this is the center. So if this right here is a radius, this one right here is also a radius. All right, the radiuses have to be the same within the same circle. So this is congruent to that. Now, if you go across from sides that are congruent, those angles are also going to be congruent. So if across from this radius R is 63 degrees, across from the other radius R is also going to be 63 degrees. So within this small triangle right here, if those two are 63, that angle is going to be 180 minus 63 minus 63. Because the angles inside of a triangle add up to 180. All right, and I get 54 for that angle there. Now, what you want to do in order to find this angle, it says you can assume the lines that appear to be tangent are tangent. Remember, the tangent angle makes a right angle with the radius. All right, so this is the one that appears to be tangent, and this is the radius right here. So this angle right here, I'm going to have to write over the 63. This angle here is a right angle. All right, now we're looking at this other triangle. I'll highlight it in yellow. Okay, we are looking at this, and this right here. So what does that mean? This angle here, the whole triangle, they add up to 180. That's going to be 180 minus 90 minus 54. Okay, I'll let you finish it from there. All right, number 14. This one appears to be tangent. So this right here is going to be your potential right. That's going to be your right angle. All right, and we need this angle here. How do we solve it? Well, we have 44 and 90 looking at the big triangle. So this one here, that is just going to be inside this triangle. It's going to be 180 minus 90 minus 44. All right, and that is going to be 46. All right, and we can see this is the center. So this right here is a radius, and this one right here is also a radius. You can mark those congruent. All right, going across, side to angle. If that angle is 46, then this angle here is 46. All right, if the sides are congruent, the angles are going to be congruent as well. So the question mark is going to be 180 minus the other two. 180 minus 46 times 2. All right, 16 is very similar. Finally, number 15. Okay, we can see these are the tangent lines and these are the radiuses, so they have to make a right angle. All right, and this right here is a quadrilateral. We can see it has 4 sides. We know the angles inside of a quadrilateral equal 360. Okay, if you wanted to see where that came from, remember the sum of the interior angles is n minus 2 times 180. So this is 1, 2, 3, 4 sides. If you just do 4 minus 2 times 180, that equals 360. So if you add these 4 angles, it's going to be 117 plus the 2 90s plus the question mark equals 360. Okay, I'll let you solve it from there. And the truth is, there's a shortcut on this one. Okay, this will always be 90 and 90. So if you have a tangent angle and a central angle, these two These two added together will always equal 180 if they intercept the same arc.